Okay. Wow, here I am thinking that now I'm the one who's out of the loop.
The word itself used to have a lot stronger meaning over time.
Okay.
It's almost like an okay. Like an okay with like an exclamation mark, that's still an okay.
Fine. I'm excited about this now. All right. I was sure this was going to be an autocorrect problem. That's interesting. All right. So, how'd the homework set go that was for today? I think this was pretty straightforward.
It's not bad.
Yeah, I mean, after some of the harder things we've done, I think this stuff about sets and probability has been no huge deal.
It's been refreshing.
Refreshingly back on solid ground kind of thing, right?
It's been refreshingly not.
That like at the end when they started asking questions about like make things like dependent and independent, and I'm still not like 100%.
There'll be more. I would say, let me see what you have, and then we'll figure out how to fix that. Because here's the deal. I think over the next couple of days, the thing about dependent and independent will get more clear. Okay. All right. Cool. Yeah. No. I think I kind of agree, but I kind of want to see what people. I'm not 100% certain that I'm going to grade. Yeah. Versus I will use it to measure how much time we need to spend on things. Yep.
Yeah, it wasn't bad once I knew what they were asking about, because I sat there for about 10 minutes looking at 25 going, what do they want?
And then I looked in the back of the book and it just said many answers.
Oh no!
Like, thanks.
I hate that. All right, I will take a look.
Some of those
Nobody's gonna grade take a tank on their grade here over this assignment. So I mean, we'll get it sorted out. I do want to take a chance today then to move forward. This is the last section of this chapter, but again, I tend to work this book in 2 chapters at a time because the next chapter goes with it really well. But this is actually the last section of chapter 7. And it's one of my least favorite things. Because it's a totally useful thing, but it's hard to figure out what kind of problem you're even using this to solve. And so we're going to pick this apart, and we're going to do some assignments on there, but I'm still digging through all the resources for teachers as to how much detail we need to go into this. Okay? I mean, this is not a probability and statistics. This is a little bit wonky and technical of a probability thing. Okay? It isn't exactly a finite math thing. It's more like if this was, I don't know, whatever, let's say that they've got a math 285's probability and statistics or something class. I'm not quite sure why we go this far out, and it is on the list of goals for the class. So I'm not quite sure how much detail they want about this. Bayes' theorem is another conditional probability thing. And it is a way of taking when you have information along the lines of if you know already the probability of event A given event B, and you have other information as well. You have things like probability of A, probability of B, and so on. How to combine all this information to get the other way around. What is the probability of B given A? All right. Like just writing it up there with symbols, it doesn't sound intimidating. It does not seem like this is such a horrible thing. Oh, I get it. So, we can write some kind of problem here where like A is the probability you have a pet, and B is the probability your neighbor has a pet. What's the probability you have a pet if your neighbor does, all this kind of stuff. And you can say, oh, what's the probability of it the other way around? Instead of given, what is the probability the person in this classroom is a girl given the person is wearing glasses? Well, what's the other probability the other way around? What's the probability they have glasses on given they're a girl? Right? It doesn't sound at first blush like this should be a scary thing. And yet, maybe it's just my brain, but this always gets all turned around for me. Okay? So I made a PowerPoint about it so that I wouldn't misstate things. And I only had to correct things in this PowerPoint about 47 million times. Okay? Because I just kept making mistakes with it here. So what Bayes' theorem is, well, actually, if you flip through section 7.6 and you take a look at it, it's going to look scary as hell. Okay? The actual thing on there, it looks pretty daunting, especially when you get to the full form of Bayes' theorem. It's got all these terms and dots and stuff in it, but it is an extremely powerful way to solve complex problems in probability. That's part of, again, I told you guys before, I actually, when I went to college, I had a double major in stats and meteorology. I mean, they have this is a unit in like a 500 level stats class. Why is it something we do in like one day? I'm not really sure why we go so deep, why we hit something that's kind of technical like this. But it is certainly a very powerful thing. And you can use it to solve certain kinds of problems. And I remember when I took a probability class, oh my gosh, like in the early 90s or something, I remember the same problem that was in your textbook. I think it was the same question. It was about, here's the classic problem. For whatever reason, I don't know why that's the problem they tend to use for Bayes' theorem, is they're asking the problem about, I hired somebody, did I hire somebody who was qualified? Because I mean, mistakes happen, right? So the problem is doing, this is example 1, I think, in your book here. It says, suppose the probability that a given applicant is hired, given that the applicant is qualified, is known. In other words, what is the probability Andrew was hired? A whole bunch of people applied for the job. Andrew's one of them. There's some probability he gets the job. Presumably, the probability is higher if Andrew is qualified, right? Because there's going to be people who apply. There's people who apply for every damn thing, right? Whether they're qualified or not. If Andrew's qualified for the job, presumably his odds of getting the job are higher than if he's not qualified, right? So let's say that's something we know. Probability that we hired the guy given he's qualified. That's something we know in this problem. That's something we know. We hired him given he was qualified. In other words, there's lots of qualified and unqualified applicants, and if there's a qualified applicant, we currently know, according to this problem, that there is some probability he's going to get hired versus someone else who might have, Andrew might not get the job, somebody else might get the job. And that person who got the job may or may not be qualified. Mistakes happen, or they lie on their applications, or whatever. Okay? So this is what we're saying here, we know this. But that's not what the problem is asking. Instead, the manager wants to know. Realistically, the manager does not care whether Andrew got the job. The manager cares whether or not the person who got the job was qualified. See, the manager wants the other way around, right? Andrew wants to know the probability he gets the job given that he's qualified. The manager don't care who gets the job as long as he's qualified. The manager wants to know what's the probability that the person I got was qualified. Given I got Andrew, what is the probability Andrew's qualified? It's the other way around. I find those hard to think about. Okay? This is the probability. He cares about the probability I get the job given I'm qualified. The manager does not care who got the job as long as they're qualified. He says, what is the probability Andrew's qualified given I hired him? Okay. These kind of problems, again, we can think about them as a glasses example that we did before. What is the probability that the person I chose in this room is a girl given the person has glasses on? What is the probability the person has glasses on given they're a girl? Right? It's a flip in the condition problem. Okay? But actually doing this takes some doing. Let's figure this out. So in this particular problem, to use the symbols that the book is using at the beginning of section 7.6, we're going to use the probability of F given E. And I'm going to leave this stuff up as long as I can get away with it on the board up here. Because it's going to be hard to keep this track. So in this problem here, we are trying to know F given E. What is the probability F, the candidate is qualified, given E, that candidate was hired? So this is what the manager wants to know. There's a whole pool of people. The manager really doesn't care who got hired, as long as that person is qualified. By the way, this PowerPoint is available to you on its learning. If you have trouble getting PowerPoints, I'll gladly give it to you in another format if you want PDFs or something. Like, I don't really know how well PowerPoints work with the Chromebooks. Also, because it's a black with white lettering on it, sometimes they don't print right. If you wanted to print them in the library or something, sometimes those ones that are dark with light lettering don't print right. I can reverse it. I mean, all those kinds of things are possible. Okay. When I was doing the online teaching thing, we usually had to make the PowerPoints available in a whole bunch of different formats because you would be surprised how many, on a Mac you can't print ones with white, or if you have a Ghost Script printer versus an Adobe printer and all this kind of crap, Trust me, so it's a problem. Okay, so here's the deal. We're going to take this information. And we're going to build a tree diagram. Here's another place where I tend to go wrong when I'm solving these kinds of problems. That's why I made a PowerPoint rather than scrambling all over the board today. Because I make mistakes on these too. The first thing, the first node or whatever you want to say on our tree is a set of branches as to whether or not the candidate was hired. So F is like Andrew got hired, F naught is Andrew didn't get hired. Here's how to be thinking about this. For your problem that you are trying to solve using Bayes' theorem, this thing up here, this will be your leftmost part of the tree. The F is to the left of the little pipe symbol, and it'll be the leftmost part of the tree. I know that rule, and I still make that rule mistake. So many mistakes have happened before. Alright, so here's our tree. Either Andrew got the job or Andrew didn't get the job. Well, a particular candidate got the job or didn't get the job. Now from there, there's that other part. Again, it's the rightmost part, it's the E, so put it on the right part of the tree. See, for each branch of whether our candidate got hired or not, there's sort of this hidden information as to whether he was qualified or not. He was qualified, E prime, he was not qualified. Or, he didn't get the job, but he was qualified. He didn't get the job, but he wasn't qualified.
Doesn't the E stand for hired?
No, E is... God. Yes, I have it the other way around. I'm sorry. See, I've already been saying things wrong? Let's back up a slide.
You just
Damn.
hold the thing up and you
Yep.
start adding them all.
Look, E, and the first branch is F. He's qualified. So, a particular candidate either is qualified or isn't qualified. See, I'm always wrong on these. I don't know why Bayes' theorem has been haunting me since like 1991. I got a 14 on this test, and it still haunts me. 20 some odd, no, 30 some odd years later, I don't know how long it's been. It still haunts me that I got a 14 on this test. Anyway, in general it was good, but this material. Alright, the other option then becomes whether he was hired. Either was hired or was not hired. Either was hired or was not hired. So, he's qualified, he got the job. Wonderful. But that only applies to one person only got the job. There's lots of people who were qualified and didn't get the job. There's lots of people who weren't qualified, and sometimes those people get the job. Or hopefully, if they weren't qualified, they didn't get the job. So those are your tree. All right. Oh man, 14, Malia. Killed me. If you think Malia's intense and works hard on grades, you should have seen me. Oh my God, I was so intense. That freaked me out.
Did you cry?
Oh my God. I still cry. I just... So, if we actually kind of added up on some information here, what is this part of the branch of the tree? I mean, I had it labeled E before, but what it really is E given F, right? This is the branch of tree where he gets the job given he was hired, right? We were already given this much, and then this is the branch where it was E given F. This is the branch of the tree where he didn't get the job given he was qualified. He was qualified, but I mean, hey, lots of people were qualified. It doesn't mean he got the job. So he was qualified, but didn't get the job. E given F. This branch of the tree is he got the job, but he kind of pulled the wool over their eyes. He wasn't really qualified, but he did get the job. Told him he had more experience than he really did. Man, did he pad that resume. Or wasn't qualified and didn't get the job. E prime given F prime. So in this rather simple case, we just had two sets of branches here, each of which only had two options. Later we'll see that there are more combinations possible, but for this rather specialized case, we just had two options for each, yay or nay. We weren't asking, did we hire Andrew or Lisa or MJ? We were just saying, a candidate, yay or nay. All right. of this crap that's on this slide here, this is not going away anytime soon. This is going to be on the next like 10 slides. But all the rest of this is just the definition of what we meant by a conditional probability. Remember, this conditional probability E given F, by the definition of conditional probability, is the probability of F, I'm sorry, the probability of F and E happening is the probability of F times the probability of E given F. That was your definition of conditional probabilities and so on. Okay. I just have that all written out there because that is how it is on page 326, so I left that information on there. All right. Let's dwell on this positive one. The candidate was qualified and was hired. The candidate was qualified and was hired. Let's just talk about that one to start with. I'll highlight it like that. All right. If I thin some space out over here for us to have some more place to write. Here's our definition of conditional probability. The probability, what we want. Probability F given E. Probability that the candidate was hired given he was qualified. Crap, do I have? All right. It's this thing we've got divided by the probability of E. But look, E can happen two different ways. E, the candidate was qualified, here, look at the numerator of this fraction. The numerator just came from this definition of this right here. The probability of F and E was the probability of F and the probability of E given F. That was something we had already on that branch. The probability of F given E. Probability of F given E comes from this numerator, the probability of F and E, and this denominator, which gives us the probability of E. Well, E can happen two different ways. It either can be F and E, or it can be not F and E. Sorry, not F and E, yeah. This one and this one. I thought I had both of these things highlighted on there, but apparently I don't. See, there's two ways probability of E can happen. You can be probability of E given F, or the probability of E given not F. Both of those are part of probability of E, right? He was qualified and got the job, and he was qualified and didn't get the job. All right? So we have this formula up here. And I say that this is a horrible looking thing, and we're going to have to get some practice doing it with simple problems first. But that is the formal statement of Bayes' theorem for the special case when there were only two options on our first choice. That first choice, where it was either, F was candidate was hired or candidate was not hired. It was a binary choice. You either were or you weren't. But we'll have other options here before, where like that first choice is what city are we going to first, or something like that. Where we had Chicago and New York and LA, or something like that. But for the special case, where there's only two options, this is one form of Bayes' theorem. And we're going to start with simple problems when we're doing this. And I thought that was called example 1 when I was doing before about that, but let's do a this is actually called example 1. I guess that other one was just in the verbiage of the text. Here's a problem. Worker errors. Sorry, my throat is really dry there. For a fixed length of time, so like in a 1 year period, the probability of a worker error on some production line is 0.1. There's a 10% chance during that year the worker is going to make a mistake. And the probability that an accident will occur when there is an error is 0.3. So you do something on the production line wrong and somebody gets hurt. Okay, there's only a 10% chance that you are going to make a mistake this year. But if you do make a mistake, then there's a 30% chance somebody's going to get hurt. Make sense? And the probability that an accident occurs when there was no error is 20%. In other words, sometimes somebody gets hurt and it wasn't anything you did. Nobody did anything wrong. It just, machine failed or something like that. Find the probability of a worker error if there is an accident. An accident happened. What are the odds it was because somebody made a mistake? See how we have one way? We already have the information. What's the probability there's an accident if there was an error? This problem already, I'm going to pick it apart in just a second here. the probability that an accident will occur given there was a worker error. Now we're asking the other way around. What was the probability there was an error given there was an accident? Okay? But, is that hard to pick through? I think so. These always freak me out. So, let's start making some notes here as to what we have in this information here. Let's give them with names here. Let's say E is there was an accident, and F is there was a worker error. How did I decide which one to call E and which one to call F? Well, of course, you could make them either way. You would just have to flip your E's and F's in your Bayes theorem. I wrote them this way because I know that the Bayes theorem formula is we're looking for probability of F given E. Right? The probability there was a worker error given there was an accident is what we're trying to solve for. So I picked this apart very carefully to make sure I knew, alright, since I know the formula is written F given E is what we're trying to solve for, I picked it apart and said, probability that there was a worker error given there was an accident. F given E. That was not easy to do though. I think I changed it back and forth like 3 times when I made this PowerPoint a couple days ago. Now I'm going to make a list of what information I have. And I'm going to highlight it as I go. Okay, one piece of information, if F is there's a worker error, okay, the probability of F is something they give us. The probability of a worker error on a production line is 10%. So that is a piece of the information they give us, because there's probability of F in this formula. We need to know that. So I'm kind of making myself a little table of what's given over there off to the left side. Another piece of information they give us is the probability of E given F. E is there's an accident, F there is a worker error. The probability that an accident will occur given there is a worker error is 30%. So that's my little table of given information right here. Alright. Picking again through very carefully. Another piece of information we have is the probability of an accident when there was no error. Probability of E given not F. And they told us that there's an accident when there was no worker error 20% of the time in that 1 year or whatever. Okay, so we've got 3 important pieces of information by picking through here. We've given the probability of E given F. We're trying to find the other way around, probability of F given E. Alright? So let's start making ourselves our tree diagram here. Alright, so I made myself some space there for it. Alright, remember, the strategy is, if we're trying to solve for, I'll write that on the board, if we're trying to solve for P, probability of F given E, make this your left part of the tree and this the right part of the tree. And so, it's a binary choice. You either did or didn't have an error. So at this point, there's only 2 branches on the tree, because this is that special case of Bayes' theorem. Later, we'll see that there's a possibility of lots of branches. And while I was at it, I tagged those branches with what their probability is. So the probability of F, there was a worker error, was 10% according to the problem, which means that the probability there isn't a worker error, the complement of F has to be 0.9. I mean, they didn't give us that information, but clearly they have to add to 1, right? Either there was an error or there wasn't an error. They have to add to 1. Okay, we have the leftmost branches of our tree diagram. So from that, we should be able to move forward to what the right branches are, which are going to be the E's. So I'm going to put the E's on here. So E's are there was an accident. given there was a worker error, there was an accident. The probability that there was an accident given there was a worker error is something they gave us in the problem. Point 3. Now, they don't tell us that, but the other branch, there wasn't an accident. Given there was an error, there wasn't an accident. Well, these two have to add up to 1. Right? Because, I mean, once we're in this branch here, either this happened or this happened. That's all the choices we got. So if this one's 0.3, this one's 0.7. They got to add up to 1. All right? We can do the same thing down here with this branch of the tree. There was no error, and there was an accident. Probability that there was an accident, given there was no error, is something we were given in the problem. We were given that that was 0.2. So this branch of the probability here, this one, once we're here, there's a 0.2 probability we're going to go this way. They got to add up to 1. You're either going off, to the no accident or towards an accident, and so the other one's got to be 0.8. See how at each node or cluster or whatever you want to call them here, they got to add up to 1. Here they add up to 1, here they add up to 1. Okay. Okay. Now we can fill all this in like they did before. What is this here? This is going to tell us, this is E given F. F happened, then E happened. E given F, which is by the definition of conditional probability, that's F. Probability of F times the probability, that tells us, rather, that E and F, I keep forgetting, that doesn't mean, that wasn't an equal sign, that tells us that F and E, F, there was an error, E, there was an accident, is this formula. Probability of F and E is this times this. F and not E. Probability of not F and E is this one. Probability of not F and not E is this one. What a mess. This is the only branch where not E and not F happened. This is the only branch where not F and E happened. This is the only branch where F and not E happened. This is the only branch where F and E. So then we can use our conditional probability thing here to make this. Alright. But as we are saying, from our fundamental idea of what Bayes' theorem means, we have all these lovely F given E's and E's given F's and so on. What we want is the other way around. We want F given E. Right? We are trying to find out what is the probability there was a worker error given an accident. Realistically, that's what happens at the company, right? Over at the Toyota line, somebody got hurt, now we're trying to figure out why it happened. Did a worker make a mistake? Did a piece of equipment fail? Whatever, right? Presumably their insurance and so on wants that kind of information. How are we going to get that? Well, we're going to use the same formula for Bayes' theorem. Again, remember, that's a special form of Bayes' theorem when that first branch of the tree or whatever only had 2 options. Later we'll see bushier trees. They're never going to get all that bushy. Alright, but we have a formula for this. I mean, all of these are things that are on our table here. So once we have this formula here, we can start picking these things off, and we can start picking these things off. Oh, I did have it here where it was. Notice, by the way, so there's this part comes from here, and this part comes from here. But these are all just values. You'd be picking them off the table here, right? I mean, you've got this number, you've got this number, you've got this number, you've got this number. You're just picking them off your tree diagram. And after that, it's just literally just cranking the numbers. And I didn't actually work through all of the numbers on there on page 337 or whatever, but you can work through it and actually find out the answer of the problem. Because it's, I mean, after that, it's just algebra. Oops, I clicked it the wrong way there. So yeah, you can just go back there and actually find out whatever the probability on example 1 turned out to be. Where did it go? It turned out to be 14%. Probability that there was a worker error given that an accident happened turned out not to be all that high. Accidents happen plenty of times for reasons that didn't have anything to do with a worker making an error. Alright, anyway, they can be done. But here's the deal, again, this form of the Bayes theorem that we've been working with, unfortunately, is sort of the baby version. But it doesn't get all that much worse, it's just the notation gets worse. I mean, this was the possibility for when you just had two options. The first choice was a binary choice.
I mean, like, the big equation makes sense because, like, it's broken down, you know, you have...
It just got more stuff on the bottom. Yeah, you're just adding more and more of the possibilities. Yep. So here's the deal. The bigger form would be when there's more... That first thing that you're... Okay, remember, you're trying to find the probability of F given E. The probability there was an error given the probability that an accident happened. But I mean, we were just saying there was an error. Maybe the probability is, maybe the first thing is, what is the probability Malia made the error, given there was an accident, versus Andrew made the error, versus Lisa made the error, versus Haley made the error, versus MJ made the error. Right? There could be 5 bushy little parts of the tree here. They get pretty darn bushy sometimes. We need a more general way to think about this. So the diagram that I'm drawing right now, I'm only putting 3 branches, and I'm labeling them like F1, Lisa made the error, F2, Andrew made the error, and there's more branches in here that I didn't draw. They were not dots here, because they got erased or something. All the way down to Fn, maybe there's 5 possibilities, whether F5 is MJ made the error. Okay? But there could be as many of these as you need. In practice, I don't know that any of them in the book ever get higher than like 3. Just because they get kind of wacky. But then farther down here, there might be lots of choices on the next node too, for that matter. Maybe there was an accident. The probability there was, well, accident, there either yes or no, there was an accident. But whatever, maybe there's other possibilities farther down from here.
What type of accident was it?
Well, yeah, maybe. I don't know. We'd have to think about that. I don't want to make a problem that then turns out to not be such a good one. So the deal is, there could be, but here's the deal. Most of the time you only care about one of the possibilities, right? The possibility, that one particular thing had happened. Most of the time on these kind of problems, you don't even need to fill in the other branches of the tree other than being aware they're there. Okay? Like, there are different outcomes that can happen. But once you do that, notice it's just the same thing we had. In fact, I literally just cut and paste the equations and then just added these subscripts to it. It's the same equations we had before, right? Like the probability of E given F1, the probability of E given F2, probability of E given Fn. Before, they were things like, instead of F2, it was F prime. Because this was either it did happen or it didn't happen. Right? So these were F primes here. But now it's just the other option, F2, F3, F4, F5. However many options you had in that first node. It makes sense, but man, is it scary. But once you have it, you can make this more generalized form of the Bayes theorem. If you want to know the probability of some particular event Fi, which is one of those first branches, the ith one, given event E happened, you just have this more general form of the equation. It's the probability that Fi happened times the probability of E given Fi, which is one branch of that tree, divided by, and then it's a big sum. The sum of the probability of F1 times E given F1, plus the probability of F2 times E given F2, keep going, keep going, keep going until you get to probability of Fn times E given Fn. Once you see it, it's not that different, but it looks horrifying. And it does raise my blood pressure a wee bit. I'm not going to lie again. But that's why we're not going to go too scary into this at this time. And I'm going to walk you through real carefully the green box on page 338. I need to get these glasses. Okay, still haven't gotten new glasses. Alright, 338, there's a box here. Let's be really careful, this is how you do it. You can't do these problems without a tree diagram, barring being like a stats grad student or something, who could probably see the patterns. That's all that I would do. Make the damn tree diagram. Okay? And you start with all the branches, and you label their probability. All those branches you will be given the probability for. That's a hint. When you're doing these problems, and they've got a whole bunch of, the probability you choose Andrew is something in this class is going to happen. Let's try. I'm going to be bold, and I'm going to try to make a problem here. Let's make F is wearing glasses. Oh no, I'm not even going to try this. Nope. I'm going to make a mistake. I can already feel the mistake coming. Alright, you're making your branches. We're trying to find the probability of F given E. Probability that we picked student Haley given we've got a student wearing glasses. Okay, but what we know is the probability of picking each of these students. We have the problem would have given us the probability. If the problem is giving you the probabilities of a whole bunch of separate simple events, those are the first branches of the tree. Because those first branches of the tree are simple events, right? Probability of F1, probability of F2, probability of F3, probability of F4. They're simple events. They're not the compound events that you're going down farther the tree, right? Where then it's E given F. So when you are looking at the problem, look for that bad smell. That is, they're giving you the probabilities of, the probability we pick Andrew is this, the probability we pick Lisa is this, the probability we pick Malia is this, the probability we pick MJ is this. They may or may not tell you the probability of the last one because you can add them all up and figure out how much you're short from one. Okay? When they're binary choice, they'll have said the probability that there was an accident is this. Because then you can figure out the probability that not an accident is 1 minus that. Alright. That's your step 1 in that book right there. Step 2. From the end of each of those branches, draw branches for event E. And label this branch with the probability that it was to get to it. Those will be probability of E given Fi. The problem will have given you those things. The probability there was an accident given there was a worker error. The probability that you're wearing glasses given you are a girl in the classroom. Okay? Those are the things, they're the compound events like that, well, the conditional probabilities, strictly speaking. I guess they're compounds too because they're ands. Will be given to you. Then, you now have n different paths that get to event E. Before we had 2 options, F or not F, so n was 2, like there was a worker error and there was not a worker error, so n was 2, so there were 2 different paths that could get to E, F and E, or not F and E. Those are the paths. Next to that path, put its probability, the product of the probability that was the first branch, Pi, and the probability that the second branch occurs, probability of E given Fi. Those things are in the problem always. Again, this table, I'm just picking exactly through on the list of things that happened on that table on page 338. And again, this is a lovely example of why the next test has to be open book and all that. There's no way you could remember that complicated formula and get them all straight and then be things reversed and so on. Yes?
Can we also have our next test be taken?
Maybe. I'm okay with that. I felt like it went well. I don't feel like there was some kind of collusion going on or something like that. Yeah. Alright. And then finally, this probability that you're looking for, the probability that event I happened given E, is found by dividing the probabilities of the branch by the sum of the probabilities of everything that leads to E. Okay, we ran low on time a little bit here, so let me show you the assignment here. Hold on. Is it today's the 22nd? Yep, so it's this one right here. Let me just crank up the font size a little bit.
Do you also want to collect our homework?
Yes, I'll collect your homework. Okay. You will notice that this is not a huge assignment. Oh, I don't have a stapler with me. I'm sorry. Just go ahead and fold it. That's fine. I didn't bring actually anything to keep track of them anyway. Yeah, Lisa.
So I have a homework that was also due last month.
Go ahead and just give it to me.
And I absent and then excused. So I did the exit ticket, but I don't know how.
Oh,
Because it
let me
wasn't.
double check on that. Here's. Molly, do you have your homework? Thanks.
I
Let me
know-
think about that.
I know it's like bell work. We can't
Yeah,
do that in-
bell work you can't do.
But my grade's a C because I missed that one exit ticket.
Okay. Well, obviously it's not going to stay that way, right? You're going to get. I'm inclined to say. I mean, how should I put it? Sierra has to take them all late,
Yeah.
and I had to make exceptions for all that. And like a lot of times, I don't get them graded right away, and I don't have any way to stop the people who weren't here from just filling it in. And so my gut reaction is it's going to be okay. I'll grade it. What happened? Yeah. Anyway, I won't explain the mechanism as to how that all works, but yeah, you'll be fine, I think. Okay. So I'm gonna leave that up there for you guys to get started. There's not that many actual problems in here. We're just gonna nibble into this right now. Okay.
Is this going to be due next class?
Yes, this will be due on Wednesday. All right. I'm gonna take this camera upstairs because I don't want to drag it to pre-calc, and you guys can get started on that.